bonus part of the homework. And to remind everybody, the bureaucracy about bureaucracy about bonus question is that there is two numbers that are the output from your homework. One of them is the total bonus points, one of them is the normal points that are counted separately and they are stored separately. The question was, you all know how we are doing, even the ones that didn't take linear algebra still know how I'm doing summation between two vectors. If this is one vector v, and at the moment I'll pretend that a vector and a point is the same thing, because sometimes it is and sometimes it isn't. At the moment, let's think that it is. Here is a vector v, here is a vector u, also think about it as a point u, and I can take the vector u, move it parallel to itself in the same length, draw it about here. So this is a copy of u once again, and then this point is u plus v. This is this point right here. That is, it's x of u plus v is just x of u plus x of v, and analogously for the y. And that's how you are adding 2 points. And the bonus question that will be actually very important for us later in the course, I'm not adding details because I don't want to give too many references, but it will be really important for us to handle the following question. If I have one convex polygon or one convex shape P and another convex shape Q, and now I pick one point of P, let's call it small p, one point at small q. Think about these points for a moment as vectors, or compute their x coordinates. And now we are looking at p plus q. Small p plus small q, it's a point. And now I'm doing like double loop, except that it runs through every possible, through infinite number of points. Namely, I check every point of P and every point of Q. So I'm doing the union for every point P in P and every point Q in capital Q. I'm computing this point P plus Q. Sum up all these points is a shape that is created at the end. Is this shape convex or not? And as a good warm-up for this exercise, do it when P and Q are both disks, and when P and Q are both squares. Try to get a feeling to what is this shape, or which is the sum of all the P in P and Q and Q in Q. And because and for homework 1, the requirement from grads and undergrads are exactly the same. Later homeworks, probably we will have slightly set of questions or some that are bonus to one population but not for the other. But right now it's just a bonus question for everybody. And we are continuing with the plane sweep algorithm. Really basic algorithm, very, very clever to my taste. Definitely our first algorithm that I think that is quite non-obvious. So our problem is we have a set of segments. Each segment is given by telling me what is the segment's endpoints. And I want to ask either are there any two segments that intersect? That's one question. Or are there, where are all the intersection points? report for me each and every intersection point. Hello? Report for me each and every intersection point between the two segments. And of course, the time that I need for it now depends on, I cannot, if this list contains n square many points in the intersection, then you cannot expect that I'll report it in linear time if there are n square many items to tell you about. So the best I can hope for in the later case is to do something that is proportional to the number of intersection points. That is, and what I'm going to pay is slightly more than the number of intersection points, but not much more. And we will make the assumption right now that no line segment is vertical, because nothing changes dramatically if I just perturb them by 0.00 degrees. I'll assume that no two segments are collinear, sitting on the same line. No three segments intersect at a common point. That's slightly harder to justify, but it's general position assumption. We just introduce a tiny bit of noise. So these three segments, if they intersected in the very same point, then after this tiny bit of noise, I'll get some different configuration of three different points. And in the textbook, in the Mark and Schwarzkopf book, you'll find a description of the very same algorithm, but with a tiny bit more attention to fine details. The very same algorithm, but where they are willing to survive with all these assumptions. That is, the algorithm doesn't make any general position assumptions. Naive algorithm, check for every pair of segments, do they or do they not intersect? N squared. Obviously. Plane sweep algorithm or sweeping line or algorithm, I'm going to sweep, remember my GeoGebra applet that I showed you last time. I'm going to sweep a line from left to right to start with as a mental thought. I'll think about this line as continuously moving, gradually, slowly moving from left to right. And at each moment, what this line needs to know is the status. I'm going to use this word quite a lot. Status will mean at every moment the line needs to know who are the segments that it crosses. Don't confuse between the line. The line is a broom you are sweeping the plane with, and the segments are the data. None of the segments is vertical, so no risk of confusing here. Horizontal segments are fine. And the status will require from the sweeping line to know exactly which segments it intersects, and it's dynamic question. It changes with time. When it was all the way here, it didn't intersect anybody. Later on, it intersect A, and then it start intersecting B, and then it start intersecting C. So at this moment, the sweeping line or the status of the sweeping line needs to know that they intersect A, B, C, and who is this? And A, C, and B, and B is the lowermost segment, above it is C, above it is A. Okay, so I need to know who do I cross and whom do I cross. So in general, the trick of the line sweep algorithm is that instead of looking at a static problem in 2 dimensions, I have segments that are not going anywhere, they are static, but they are in 2 dimensions. I'll prefer to work with a dynamic problem, but in 1 dimension. That is, I'm only focusing on what happens on the status itself. That's my only center of attention. But this is dynamic, that changes as the sweeping line moves. So there is a lot of questions here that I must answer of how do I handle how do I know what happens at each time, and how does it help me find the intersection points, etc. All coming up. Okay, so my first observation that I showed you with a Java applet in a more dramatic way was that if the sweeping line only needs to know what are the segments that it crosses and at which orders, I can, and I'm moving a bit, like I'm moving in from here until here, and between these two steps, I did not start intersecting any more segments. I did not stop intersecting any more segments. The order of the segments did not change. The order of the segments whom do the sweeping line crosses here are my three segments, A, B, C. Here is my sweeping line, let's say at x1. Here is my sweeping line slightly after at x2. x1, you can think about it as time 1, the same sweeping line at time 2, x2, and what happened between x1 and x2. Remember, status knows which lines, which the status, and it's a word, don't try to make sense of why we called it the status, because the status is this part of the algorithm. There will be a data structure that will help us in this to know it, but the job of the status is to know what are the segments that are crossed by the sweeping line L, and at which order. Lowest one, the one above it, the one above it, and so on. So what happened between x1 and x2? The line sweep didn't start intersecting any segment. The line sweep didn't stop intersecting any segment. It crosses exactly the same segments, and the order between them did not change. Meaning that instead of gradually moving the sweeping line slowly from point continuously in the plane, I'll be motivated by generating events. The sweeping line will jump from one point to the next point to the next point, always from left to right, and I'll only care for events, and only events at which the status need to change. If I have some intervals between x1 and x2 that there are no changes in the status, then I don't need to stop there. It is not an event. So what type of events are we going to experience? It might be that the status start intersecting B, and that would be an event, what we'll call the birth event. There are plenty of slides that will explain it in more details. The status starts to intersect B, which will make it a birth event of a segment. As the status moves further, it might hit the right endpoint of A, which will be the death event of A, hitting a right endpoint of a segment. Remember, no vertical segments, so you cannot be born and die immediately at the same time. So birth event. Another event will be hitting the right endpoint. And another type of event that comes from the restriction that the status needs to know at which order it crosses the segments from left to right, which means that now if actually there is also a segment D and D crosses B, then this intersection point between B and D must be an event as well. Why? Because the order changes at this point. The order before the crossing was C was the lowermost segment, above it was B, above it was D, and above it was A. What happened immediately after the intersection point? The order between B and D has changed, so the status must know about it. We need to update the data structure that keeps the status happy. And there is still plenty of technical questions that I owe you about how do I handle this data structure and how do I know which events are going to happen. Okay, so sweeping the plane with this line motivated by events. Sweep from vertical line from left to right. By the way, in the text in the MMMS, the sweeping line is from top to bottom. No difference otherwise. It's the same thing. Sweeping a vertical line, conceptually replay as the x coordinate is just the time, moving it from the leftmost point of t equal minus infinity, x equal minus infinity. And and maintain a dynamic set S of segments. S here is both for set and for status, capital S. And this dynamic set S stores for us what are the segments that intersect the sweeping line and at which order they intersect it. That is, and this order should be based on the y coordinate. Right? C is the lowermost one. No matter where I'll pick exactly, the intersection point with C has the lowermost y value. The lower you get, the smaller the y value. And the order changes when a new segment is encountered, the segment is born, that is left endpoint. A right endpoint is encountered, that is the line sweep just hit the rightmost point of a segment, it's the exiting or the death event. And the third type of event is two segments intersect, cross each other. Okay, so my first attempt is to move from a continuous world where any x value is a good place for the line sweep into this set of events, a discrete set. That is, I'll make the status jump. Hello? I'll make the status jump from one event to the next event to the next event, and I'll be very careful not to miss any events. Let's think about how do I generate the events. Some events I know about ahead of time, and some events I'll discover on the fly. To be more precise, all the birth event and the death events, left endpoint and right endpoint, all of them I know ahead of time. So in this aspect, I can think about all the events as a set of x values that I just need to know at which order to scan it from left to right, with x equal very much to the left until x equal very much to the right. How many events of this type of birth or death do I have if I have n segments? Not a tricky question, but still need an answer. How many events of the first two types? Either birth event, the line sweep hit a leftmost endpoint, or death event, The line sweep hits a right endpoint. Sorry? 2n, exactly. Yeah. Segment has exactly 2n intersection, and it's exactly 2n because of general position tells me that I don't have any two events that happens in exactly the same x. But every x will be just for one particular x. So there are two endpoints, and I need to, one option is to sort them ahead of time. Another option is to use priority queue. Priority queue, also known as a heap, sometimes binary heap, is a data structure that hopefully all of you covered in 345, but is very easy to remind everybody. There is a chat, is a data structure that have the following example. That's an example of a heap. It looks like a binary tree. Oh, it is actually a binary tree, but it's not a search tree. There is no much importance to what is in the left child and what is in the right child. Instead, the order is what's called a heap order, namely each node is larger than its parent. That is, the key in each node is larger than the key of the parent, of course, if it has a parent. That is, 50 is larger than 14, 32 is larger than 14, 73 is larger than 32, which in turn is larger than 14, and so on and so forth. That is, I don't care about left-right, I just cared about a relationship between parent and child. And binary heap has a few beautiful properties. It's really fantastic data structure for the thing that it knows to do. Its height is log 2 of n, log to the base 2 of n. That is, its normal binary search trees, its height is a constant times log 2 of n. Here we are really as compressed as possible. It's log 2 of n. It supports operation as report mean, which takes constant time. Why? How do we do it? How do I know what's the minimum value in this heap?
It's in the root.
It's always in the root. I mean, definitely if it's unique, or it's always in the root and maybe in other node. So I just need to access the root, and that takes order one time. I can extract the mean. And I refer you to CLRS for further details, or one of the books that I really like. That is a book on data structures called Dennenberg and Lewis. Check it out on the website of 445. Can get it used for $1.72 last time I checked, which is, and you can For whichever reason, there are plenty of them, and it's a fantastic book. The new one is a bit pricey. Yeah, extract mean. How are we doing extract mean? I want to get out from it the minimum, so I'm taking the 14 out. The rule of the heap says don't leave any node unoccupied. So I'll have to take some node, and the rule of the heap says take always the key from the which is the leftmost key, which non-empty, the non-empty rightmost key on the lowermost level, which was, what was it, 62? So the 62 is going up and replace the parent and replace the root, so the root is not empty. And now the new root needs to check if it creates any issue with any of its children. It looks on its left child. Is 62 smaller than 32? No, it's actually larger. Is this smaller than 50? No, it's actually larger. So 62 will be replaced with the smaller of the two children. So that's why we don't destroy the we pick the smaller one. In this way, the relationship of parent-child are still preserved. So 32 will go up, 62 goes down. I'm sure that the 32 is indeed smaller than 50 because that's how I picked it. On the other hand, on the right, on the left subtree, I might created some situations that I need to fix. I'm checking if 62 is smaller than both its children. Well, it's smaller than one, but not from the other. So I need now to replace the 62 with 60. So sorry about it. Sixty goes here. 62 replace its place, and now the heap is fixed. So extract mean takes order of log n, and the constant is really small. That's why it's so fast. They are very fast operation, much faster than a binary search tree. And similar idea will tell you that you can do insert in the same time. So you can report the mean, you can extract the mean in log n, you can insert a new key. Insert new key will also take log n. Very similar idea, and it really helps us in the search, in the line sweep algorithm. Because why does it help us in the line sweep algorithm? The reason is that, if you remember, I'll go to the slides. What happened here? I have a set of events. Some of them I know ahead of time, some of them I discovered. Let's assume that I know about all of them ahead of time, just for simplicity. Let's insert all of them into the heap. And now I'll ask you, when my line sweep moves all the way from left to right, when my line sweep moves all the way from left to right, what is the first endpoint that it meets? What is the first event that happens? Well, that's obviously among the events, that's the one with the smallest value. What is the first event that I meet? It's the one with the smallest value. But that would be the birth event of C. What is the next event? Well, the next event will be the birth of A, which I know how. it will be the smallest among all the events which are not processed yet. The second event going through the endpoint of A is just what? The smallest event among all the events that are not processed yet. So when I'm hitting an event like the birth event of C, I'm performing extract min from the heap, remove it from the heap, so I will not have to process it again. And then the minimum in the heap is just what the next event is going to be. And you process it and you extract the next event and the next event and the next event each time you find it by just asking what is the minimum of the heap, and once you process it, you're deleting it, extracting it from the heap. So knowing about each such event, at least from the priority queue point of view, it will take logarithmic time. Now, if I don't have any intersection between segments, then these will be all the events that I'll report, only the starting points and the ending point of the segments. So you are just doing heap, just can use heap in this way. And the reason that I prefer the heap over other type of sorting is that if I do have intersection points, then on the fly I'll discover more events and I'll have to also insert them into the heap. You'll see how it works. So far there is plenty of things that depends on each other, and it's a bit harder to understand what's going on because each one, there is no clear correct explanation of how to explain everything. Everything is depending on everything else. I'm talking about events, but it's very hot, airy hand waving. I'm talking about status and priority queue, but it's also hand wavy, and but we'll get there. Everybody will understand. Trust me. By the way, a few times, what was it? A year and a half ago, several times I gave implementation of the line sweep algorithm or some variant of the line sweep algorithm as an exercise in 345 in data structures. There were some simplifications that I did, but basically a very similar algorithm is really easy. I found it completely fine as a homework in data structure course. Okay, sweeping line left to right. Talked about it. Yeah, each time I'm going to the each time I'm moving to the next event. Definition: the status S, we already know it, is a list of segments that the line sweep L intersect at this very moment. Things are moving, things are changing in time, in the order from bottom to top. That's exactly the status. An event definition happens when the status changes. That is, either a birth event, a segment is born, a death event, a segment just died because this line sweep just hit its right endpoint. So it should not, as far as the status concerned, the segment is of no interest anymore. And the other type that we'll discuss later will be, of course, the intersection event. Now, what the status is not storing, what the status is not storing, it never stores explicit y coordinates. Again, it never stores explicitly y coordinates of any segment because the y coordinates changes over the time. The exact intersection point changes over the time. What the status needs to store instead is the names of the segments that it crosses in the correct order. Sorry about it. Yeah. in the correct order. So the status that A is just going to be born, the status before it contains the name of the segment, pointer to the segment D. That's the lowermost one. Above it is a segment B. Above it is a segment C, and A is just about to enter into the status in the right place between B and C. Okay, and what I store is the exact is just the names of the segments, which would mean that at some point maybe I need to change the status because segments are born or die or cross each other. So once again, we just jump from one event to the next event, to the next event, to the next event, because between events, nothing is changed in the status. Nobody dies, nobody born, the order stays the same between events. Only in events is the only places where the status is changing. Of course, had I care about the exact y values, then I had to store infinitely many values because the y keeps changing all the time. And as you saw, that was an example of that was an example where I have also an event through intersection points. Right? There is an event through the intersection point because before the intersection point, the lowermost was F, above it was B, above it was D, and above it was E. And the intersection points means that B and D swaps their order. That's exactly what intersection point is. Okay. Highlight of the algorithm, sweep a vertical line L from left to right, and each time that L meets an endpoint, update the status. And here is a new thing, check segments intersections, but I want to be careful about which segments am I going to check, who is intersecting whom. So the checking for segment intersection is the heart of the algorithm. So let's see how I handle the birth event. The line sweep just start intersecting the segment A. It already intersecting D and B, so the status from up to bottom to top is D, B. A will be just here in the middle, and then C and E. And what do I do when a segment A is born, just inserted? I'm adding the segment A to the status, of course, and now I'm going to check intersections, but between whom? I'm just looking at the immediate neighbors of A on the status. That is, A needs to know only on its immediate neighbors. A is looking upward, looking to the sky, and A sees just above me C is sitting. I see C just above me. A doesn't know anything about E. E is not an immediate neighbor, and C is an immediate neighbor. Similarly, A doesn't know about D, however, it does know about B. The immediate neighbors of A at this moment are C and B. Okay, everybody is feeling convenient with the notion of immediate neighbor. From now on, every time that I say neighbor, I mean the immediate neighbor. Immediately above me and immediately below me. I don't see through a segment. Segments are opaque. And I only care for intersections between immediate neighboring segments. My invariant will be, I know about all the events that happens between segments which are immediately neighboring. Now, of course, not every segments have two neighbors. Some of them, like D, have only one immediate neighbor. B is the only immediate neighbor of D. And when B was born, it didn't have neighbors at all. Okay, so back to the description of the algorithm. We add the segment A to the status S. The status is not the priority queue. Status will be a different data structure. I'll check intersections between A and its immediate neighbor. That is, I'll ask, hey A, do you cross C? And if yes, what do? I insert them as future events. I'm going to my heap and says, hey, I just found out that somewhere in the future, C and B are going to intersect. I'll compute at which X value, which time it's going to happen in the future, and I'll insert it into the heap. You don't see it, but every number here has auxiliary, has satellite data that says it's an X value, that's a key, 32 is a key, the X value, but associated with this is a satellite auxiliary data that says what type of event is this, from which segment did it come, is this from the is this event of type birth event or death event or crossing event, and if it's crossing event between which segments. So every key that you see behind me is associated with the segments that are involved. So once again, when a segment is born, it checks intersections only with its immediate neighbors. As you see, A also intersects with E, but we don't know it yet because they are not immediate neighbors. We only know about the intersection of A with its immediate neighbors, that is C and B. And at this point, by the way, we also know about the intersection between D and B, this intersection point, because they are already been born and they are neighboring. Okay. What happened when I hit a right endpoint of a segment? My line trip just hit to the right endpoint of a segment. So let's meditate a bit about the invariant. I need to know about every intersection point between every pair of neighboring, highlight, neighboring segments. Need to know about every intersection point between every neighboring segments. What happens when A dies? Well, what's the status of C and B? C and B. When A was still alive, then A separated C and B. They were not immediate neighbors. I'm hitting the right endpoint of A, implying that they are becoming, C and B are becoming immediate neighbors. So what is my uncontrollable reflex to do when I see that two segments just becoming neighbors? Every time that I see that two segments are becoming neighbors, I'm asking, do they intersect? Is the intersection in the future? Because if it's in the past, I never move my sweeping line backward, I never move it to the left. I'm asking, there are two segments that just becoming neighbors, C and B in this case. So becoming neighbors at this point, I'm asking, do they intersect? And if they do intersect, then they intersect in the future, then insert it as a future event into the priority queue, into the heap over here. Okay, so in terms of the status, I delete A dies. During the deletion, I'm asking who is a successor and predecessor. Successor is the smallest value larger than A, that is, who is just above A, namely C. But successor is just the smallest value strictly larger than A. Who is a segment just immediately above A? It is C. Who is a segment just immediately below A? It is B. These are the two neighbors, B and C, two neighbors of A. Check for intersections between them, and if there are intersections in the future, insert it into the heap. Okay, what should I do with the third types of event? I hit an intersection points between C and B, and I'll repeat my uncontrollable reflex. Even write it. This is my mantra for all types of events. Every time that some two neighbors, S1 and S2, are becoming neighbors, immediate neighbors, we check if they cross each other, intersect each other, and also if they intersect in the future. And if yes, we put it as an event in the priority queue. So when my line sweep hit to a crossing event, what happens? I need to report it if my goal is to report all the intersection points. And I also need, I have new pairs of segments that just becoming neighbors, correct? B didn't used to be, at least not recently, B and E were not neighboring each other. B and E were not neighboring each other, not recently. However, after the intersection points, B and E are neighboring on the line sweep. Everybody agrees? Maybe I'll do another diagram. Let's look at the point Q. A didn't used to be, when my line strip is right here, that will be L1, A didn't used to be a neighbor of C. A was not a neighbor of C. Possibly they used to be neighbors, possibly not, I don't care. But currently they are not neighboring of each other, A and C, because B is stuck right there in the middle. Analogously, D and B are not neighboring each other. What happened when I hit the intersection points? The order between B and C is switched. So C is becoming a neighbor of A. C and A are becoming neighbor. Check for intersection point. That's the moment at which you're discovering the future intersection points between C and A. That's exactly when they are becoming neighbors. What about B and D? Well, B wasn't a neighbor of D because C was stuck in the middle. When I hit Q, B is going downward, and now B and D are becoming neighbors. And I check if they intersect in the future, and if yes, we find yet another future event, namely the intersection of B and D. I think that it's very cool. Sorry. Okay, so when I hit an intersection point, don't confused, the intersection point is between C and B, but at this moment I figure out that B is becoming a neighbor of E. How? Because I'm just checking who is a segment immediately above the intersection point, and similarly the segment, if exists, immediately below the intersection point. And of course, what happened to the status? Immediately after the intersection point, the status is changing before and after the intersection point, right? The status before was D, C, B, A, and now that was the status before from top to bottom, from bottom to top, sorry, and after that S prime. D is still the lowermost one, but just above it is B, above it is C, and above it is still A. That is, A and C swap their order. And as before, every time that a new neighborhood is appearing, check for intersection point. If there is intersection point, place it in the priority queue, if it's future intersection point. Okay, so here, check future intersection point between S1 and its new neighbors. If exist, insert this event into the priority queue as a future event, and repeat it. That is, check for intersection point between S2 and its new neighbors. C in this case, C doesn't have anybody below it, so it's a bit, there is no way to continue. Claim I don't miss any future events. I don't miss any intersection point. That's what the theorem is trying to prove. It is that through this algorithm, I will not miss any intersections between segments. Why? The theorem says actually a bit stronger. If two segments C and B intersect at a point Q, and remember, no vertical segments. If they intersect at a point Q, then of course, because both of them are non-vertical, then they must be alive slightly before Q. Remember, general position also means that one is not born at the intersection point. Another way where we are using the general position assumption. That I'll assume right now that this case of that the intersection point is also the birth event doesn't happen. Once again, if I don't make this assumption, it doesn't make the algorithm any harder. Maybe it just paying attention to these cases as well, but everything else is completely correct and is just as complicated, and it's just as simple. Okay, so obviously, if there is an intersection point of Q with C and B, then there will be some moment before I hit Q that are neighbors. But what the theorem says is a bit stronger. Not only that there is time that they are neighbor, but there is actually an event that happens to the left of this intersection point, to the left of Q, at which they are becoming immediate neighbors along the sweeping line. There must be an event prior to Q at which C and B are neighboring. Right? And obviously there is some time. If I just move slightly a bit to the left of Q, they must be neighbors, otherwise they don't cross, and they both exist slightly to the left of Q. But the heart of the proof is to say that there is an event from some type. So let's C is born at some point, B is born at some time. Let's assume that C is born after B. That is, the left endpoint of C happens after the left endpoints of B. That is, when I hit C, when my line sweep L hits C, B already exists. It's already intersecting the status. Okay. Otherwise, I just in the proof I just switch the rules. WLOG means without limitation of generalization. Right? Because if it's not the case, then I just sweep who is B and who is C in the intersection. Okay, so I'm thinking about the birth event of C. B exists. Our theorem says C and B intersect at some point in the future. Possibly they are immediate neighbors right now, and then I discover Q. That's the event that I discover Q, if they are already neighbors. Or possibly they are not neighbors at the moment where C is born. How come they are not neighbors? There is another segment, let's call it A or A prime, that separates right now when C is born. A or A prime is separating between C and B. And now is a place where I'm going to use the fact that my algorithm works for things that are X monotone. What is X monotone? X monotone means that every vertical line crosses these things only once. Segments are a good example. This line will be a good example. So that's good, that's good. Not X monotone will be something that can turn around and comes back, because this one is crosses by a vertical line twice. So this is non-X monotone. And by the way, what you know about functions, if a function is both X monotone and Y monotone, then it's just normal monotone. But here is a point of the proof that I'm using, that segments are not X monotone. Because what happened with this A or A prime that separates between B and C? Well, it continues to the right. It cannot now turn around and come back to the left. So what's the option? Maybe A prime just die before it gets to Q. Right? Maybe A prime that separates B and C just die, it's a right endpoint, and this will be the event at which I discover that they intersect. What's the other option? Here is B and C. And I have this annoying A coming from the left, sorry, and it separates between B and C. It separates until what? It cannot turn around. That's the monotonicity. So either it vanishes to make them all meet, or the other option is that it must intersect either B or C. Correct? I mean, it's a bit hand-wavy. It's easy to make it into a completely formal proof, but it's convincing enough. Right? If you think about this triangle where A is separating between them, then the segment A is entered into this triangle. It must exit somehow, or it must die inside this triangle. So the other option is that A intersect, say, B, but this is an event at which exactly B and C are becoming neighboring to each other. Or unless there is another segment that separates them, but then everything that I said by induction holds for this other segment, A double prime, that separates between them right now. But whomever are this, but all the segments that separates between B and C at this moment, each one of them must either terminate or crosses either B or C in some intersection point. Look at the rightmost such event that happens to the left of Q. That's the event at which C and B are immediate neighbor to each other, and that's where I discovered that the future crossing event between them. Okay, so the algorithm will find out all the intersection points. I'll never skip over an intersection point. How do I maintain the status? That's exactly where I'm using the exercise that we played with last meeting. Right? This exercise that we played with asks you have a vertical strip, sigma, vertical strip, everything between these two vertical lines. You have a set of segments, non-crossing segments, call them A, B, C, D, E, and the question was to perform binary search between them. I'll give you a point Q, and I want to ask who is a segment just above me, who is a segment just below me. And what is this strip, the sigma right here, when I'm applying it to the algorithm? That's just the area between two consecutive lines between two events, two consecutive events. There was some event that symbolized the beginning of the strip, the left endpoint. There is some event, maybe crossing event, that specifies the end of the strip, the right endpoint, but in between the left and the right, nobody was born, nobody died. Otherwise, there would be another line strip in between. So when we discussed it last meeting, I suggested to keep the segments in an array. However, we never store the exact y value. Instead, we store the name of the segment or its endpoint or the line through the segment. And then if I know what is a line through B, if I know what is a line alpha x plus beta, the line that contains B, check the details from the last meeting, the line that go through B, and you give me Q, then I'll ask what is the x, y coordinates of Q, Q that have x and y coordinate, and then I'll take the x value, put the x value of Q, that is Q dot x multiplied by L alpha plus beta is this larger or equal, larger or smaller, larger, equal, or smaller than Q dot y, the y value of Q, telling you if you are above, on, or below the line. Now, I'm doing almost the same thing with the status, except that I need to be able to insert and delete segments into the status. Segments are born and die. So instead of instead of an array, I'll store them in an search tree, balanced search tree. AVL will do, red black will do, 2-3 will do. At data structure at 345, I let them implement skip list, which is just giving you the same performance as just much quicker, much easier to implement. If you don't know about skip list, check my slides, my lecture about it. Fantastic data structure, also gives you log n for operation. And now, how does it work in particular? Well, let's look at the segments A, B, C, D, F in this order. That's the order at which the segments are stored in the tree. Every node stores a segment. A is the smallest one because it's the lowermost segment. D is in the root of the tree. D right here. F is the highermost one. And now let's think about a birth event. G was just born. G was just born. It needs to be entered into the tree. I need to find out where to insert it. What do I do? Just perform normal search in the tree. Namely, I'll go to the root of the tree. The root of the tree stores D. And I'm asking, hey, the left endpoint of G, is this above or below D? Is above or below D? It happened to be above D, so the newcomer needs to be, G needs to be on the right subtree. Above meaning larger y value. I'm going to the right subtree of D, F lives there. I'm asking F, the new endpoint, above or below F? Answer, it's below F, so the newcomer is going to be in the left subtree of F, except that there is nobody to the left of F, implying, like in any normal binary search tree, not even balanced, that the newcomer G is going to be in the left subtree of F. Okay, so what on the whiteboard in last meeting was a query point Q, that's a rule of the left endpoint of the segment G. However, the tree contains, as before, segments with whatever information that you want about the segments, and once again I'll say it not exact y value, just the name of the segments, and the order of the tree is the order of the segments from bottom to top. That's important. The tree is always sorted in the order of the segments from bottom to top. Okay, so how much time does it take to insert a new segment? Just as in any other balanced search tree, order of log n time. But you can next, if the tree is not balanced and it's say AVL tree is a difference of heights of the left subtree and the right subtree is the difference of the height is at most 1, either -1 or 0 or 1. So, and there are simple rotations that will fix the tree. If the tree is not balanced after the insertion, then simple left-left or right-right rotation will make the tree balance again, which will give it a height of order log n, which means that insert and delete and successor operator and successor and predecessor can all work in log n time. Let's define it once formally. If S is a set of keys K1 that is smaller than K2, that is smaller ... smaller than Kn, and I have some value X that might be in the set or might not, I don't care, then the successor of X is the smallest Ki, which is strictly larger than X. Smallest value of K that is strictly larger than X, and it might be that there is no successor, and the predecessor would be the predecessor of any value X in the set or not, is just the largest Ki, which is strictly smaller than X, and null. And every search tree with any amount of self-respect can support successor of predecessor, each in log n time. Think exactly how you can, anyway, search tree, you can also find the successor in log n time. I'll give you a value 17. I'm asking what is the element in the tree which is the smallest but larger than 17. You can search the tree and find it in log n time. Okay, so we are almost done with the algorithm. So the operation on the tree are insert a new segment S into the tree, insert the segment S into the tree, delete a segment. Why do I delete the segment? Because I hit its right endpoint. Also in log n, above in T of the segment S is just return the segment just above the segment S. Of course, the segment S at its intersection with a sweeping line right now. With the segment just above me. By the way, you can even keep the tree linked, and then every such operation takes constant time of above and below, because you're keeping it also sorted as a linked list. And above me is just successor. Below, analogously, it's just the predecessor operation. Also goes in log n. So in particular, I can ask who is a segment currently just below C, and it will take log n time. So once G appeared, all I need to do is, insert it as a new element. Okay, here let's summarize it all. We have 5 minutes. It probably will be enough. What do? I start when I don't know about any intersection points. My input is a set of segments. I have a set of segments, so I'll sort the endpoints of all the segments from left to right and insert them into the queue. I'm using queue as a priority queue as a heap. Queue here stands for the priority queue, the one that is sorted based on X. The elements of queue are sorted based on X from left to right. So far I covered all the events which are birth event or death events. I still don't know about any intersection points. For each event P which are in queue, in which order? From left to right. That is, how do I do it? Each time I pull the smallest key from queue. See, there is a lot of moving parts here. It's nice how they all work together. So for each event P in queue, arranged from left to right, do what? If P is a left endpoint of a segment S, then you need to insert it into T. T is what sorts the status. It is sorted based on Y. Priority queue sorted left to right by X. T, the tree, sorted based on height, based on Y. So if above of T of S exists, I'll just call it above T of S, there is somebody above the newcomer S, and if it intersect S or below T of S exists and they intersect S, there is neighbors of S either from above or below or both, then insert these events. There might be 0, 1 or 2 such events. Insert them into the priority queue, into the heap, as future events. You'll process them later. Right now we are processing P. Future events will be processed later. That was for the left endpoint event. Else, if P is a right endpoint of S, we hit the right endpoint of a segment, the segment S just died, then what was the case? S just died, which makes A and B neighbors to each other. A and B just became neighbors to each other. So if both above T of S, namely if S has a neighbor from above and also a neighbor from below, maybe it doesn't have, but if it has neighbor from above and neighbor below, then check if they intersect. A and B are not doomed to intersect, but if they do, that's the time to find it out and insert this event into the queue. Right? It will be a future event between this event Q prime and the current event. The current event is S just died. Until the future event Q prime, there might be billions of other events from all types that will happen until Q will happen. That's why I insert it into the priority heap, into the priority queue, the binary heap. And every such insert just takes log n. So if there is somebody from above and somebody from below, then check if they intersect, and if they intersect, then insert it into the queue, and of course delete it from the S. Last case, if P, the event that we are handling, is the intersection point of two segments S and S prime, then report it. The algorithm needs to store, report, tell somebody about all the intersection points. They both continue to exist, just their order on the status swapped. How do I change the order in the status? I'll delete one and reinsert it. Just perform delete and reinsert. There are other ways, but at least if you want to just recycle code that you already have, delete and then insert. But there are other tricks as well. Okay, so switch their order in the status, the trees that's sorted based on height. Each one of them has now a new neighbor. I mean, one neighbor of S is still S prime and vice versa, but each one of them has a new neighbor. Remember? Here is S and S prime. And here is A and B. So S prime is becoming a neighbor of A after the intersection point. Check if they intersect. If yes, place this point into the priority queue. And similarly for S and B, they're just becoming neighbors if they intersect. Insert into the priority queue. And that's it. And you are done when the queue is empty because you processed the last event. People, questions about it? So next class, the only thing that is left is just to convince you that each operation here, each event takes order of log n. Takes order of log n to process this event. It might be birth, it might be death, it might be swap. The order might hide here a few elements that were inserted, a few elements that were deleted, but it's a constant number. So the overall running time is order of n log n that I have to pay because I sort all the segments. That's unavoidable. That's for the endpoints. Plus k, the number of intersection points, log n. That is, for every intersection point, you're also paying log n. So you're getting order of n plus k, which it must run no matter what, times log n. Now, if you just want the algorithm to tell you either any intersection points or not, you don't need to know about all the intersection points. You just want a yes/no answer, then you are running the same algorithm until you find the first intersection point and then you stop. You don't process anything. So it's just n log n. People, questions?
I had a quick question. If there was two segments, A and B, and they were initially neighbors and they intersected in the future, it'd get added to the queue. What would happen if there was a segment in between them that was born and died later? So they would check again, and therefore after that segment died, you might have to check if there's an intersection again. Oh, yeah.
So you just answered yes. The same either I'm careful to delete it, or I'll say that there are a few segments. That's an excellent question. We'll get back to it again, but just to tell everybody, and I didn't get the name. Who asked it? Marco. So excellent question of Marco. That let's look at S and S prime, and let's ask, do I discovered, let's say, when they were born, then they were separated by this guy, but then they become neighbors, and then they got separated and got neighbors again. So I found the intersection point more than once. Possibly I find it n times the very same intersection points, but now I'm using the fact that I don't have any two events in the same x coordinate. So all these events have the same x coordinate, so I reported it once when I get to Q, and I see that the next event has exactly the same x coordinate, so I just not report it the second, third, fourth time. It's a very simple hack when you have general position. If you don't have general positions, then you need to sort it a bit more cleverly, but again, yes. Now, it might be that you'll store, it's not obvious that linear memory will be enough. That's a much harder question. It is still true, but it's much less obvious that the only linear memory is sufficient. because, as you said, the same event might be stored several times, but we'll discover it only when we'll get to it. Other approach is to say we are using priority queue because it's so efficient, but you know what? Binary search tree also support insert and delete in log n time, but binary search tree, as opposed of heaps, binary search tree can also do find, which means that I can, before I insert this event, I can find is it already inserted or not. That's a different idea. It's still log n. I'm losing some of the elegancy of using binary heap. Instead, I'm using binary search tree. And I'll say Q is already discovered. Before I reinsert Q, I find to check if it's still already in the heap as an event or not. And then if it's already in the heap, I don't double insert it. Okay, did I answer? And thanks for the question, Marco. It's an excellent point.
Yes, you answered it. Thank you.
Anything else? Okay, thanks. There was a strange bug with the calendars of the course, but so I'll reinsert all the dates again. Your homework didn't change still on the 8th, I think. Yeah, bye everybody.